Hi, and welcome to another lecture in the Artificial Intelligence lecture series. In the last video, we talked about analytical solutions for linear models. And in this video, we are going to look at using gradient descent to arrive at a solution for linear models. So let's first see the theoretical background of this, and I will briefly explain what gradient descent is. So before coming to gradient descent, let's cover a little bit of the background. So you probably remember that in the last video we mentioned how we can represent a linear model in form of this equation: y equals wx plus b, where w are weights and b is our bias, and y is our dependent variable and x is our independent variable, right? So using this equation, or assuming that this is our model, we then approximate some values for w and we approximate some values for b. So having approximated these values, then we can use our x, which is known. So let's say w1 and b1 are approximated weights and are approximated bias. So then we can arrive at y hat, which is our predictions. So now, like, we have arrived at our predictions, and how do we know that our prediction is correct? So that would depend on the difference between the actual y value and our predicted y, right? So we need to have some kind of a comparison to see how far away we are from the solution, how off are we. And by examining this, we assume that we can maybe even further improve our values for w and maybe improve our value for b as well. So we can arrive at maybe an even better prediction. Can we then compare this y2, let's call this previous one y1, can we then compare both to the true value and say which model is the best? So this is basically the idea. We'll arrive at one model and then we'll try to improve it little by little, right? So in order to discuss this, we will first consider a simpler problem than last week's one. So in this problem we are going to look at today is about predicting the value of a house based on some of the features. So in this dataset we'll be looking at, we have data, of course, related to the price. So this is called I think this is just called the housing prices dataset. So this is called the housing prices dataset, and of course we are given the price, and we are going to predict this as a function of the floor area of the house, the number of bedrooms, number of bathrooms, number of stories, whether is it close to a main road, whether there is a guest room, whether there is a basement, whether there is hot water, whether there is AC, whether the number of parking, spaces, and whether it's furnished or not. So you can see that we are considering quite a lot of features, and I think there are a couple of other features as well, and we are going to guess the price. So this is a regression problem, because the price is it is a single value and it exists in the number line, and we are going to approximate that value in the number line based on these features that I've described here. So going back to our mathematical representation, so we have our y hat, which is our prediction, and we have our y. So how are we going to check whether our y hat is close to y or not? So we are going to use an error metric. So we'll consider the mean squared error as our error metric today. So mean squared error is equal to the squared error, and then we take this error for all the samples. So we take the error for each sample, square it and sum it, then divided by the number of the samples. So basically the mean of the squared error. So now we know the mean squared error. What we need to do is to minimize the mean squared error, because we know how to calculate the mean squared error. We know n, we know y, I, which is the true values, and we know how to calculate the y hat. And we know further that y hat is equal to wx plus c. So we should be able to change the values of w. Why did I call it c? It's b. So we should be able to change the value of w and b, and in doing so we should be able to change y hat, and in doing so we should be able to change y hat in this equation, and as a result change our mean squared error. So this is the idea behind the gradient descent. So let's try to visualize it a little bit, like a very simple visualization. Let's say we have our loss here, and let's say that just a single value represents all w's and b's, right? So this is not as simple as this, but for the sake of explaining, and for the sake of explaining again, imagine the loss function exists in a curve similar to this, right? So let's say for our first w1 and b1, the calculated loss is here at L1, but we know that where we ideally want to be is at L min, which is, let's say, okay, let's call it w min and b min. So now this is a little bit more simpler to explain. Oops. So now we are here, but we want to go here. And how do we do that? For this, we will consider this process called the gradient descent. So this is a little bit similar to hill climbing. So imagine you're on a hill. So let me try to find a photo of a hill. So let me try to find a photo of a hill. Okay, I'm getting an image out of Wikipedia, so hopefully that's free to use. Not the best quality here, but imagine you're at a certain location like here, and you want to get down. So what you would be doing is you'd be looking around and thinking, okay, which way should I go in order to reach the foot of the hill? So you'll think, okay, I will go in the direction where the slope is the highest. So this may not be safe, so don't do that if you're on a mountain, but you'll think, okay, in this direction the slope seems to be the highest, so if I go that way we'll be able to reach the foot of the hill real fast. So that's what we are going to do. So and the hill analogy works a little bit better because in reality the solution space does not look like this. It's much more complex. So if I'm to try and find a more complex solution space, it will be in the shape of a paraboloid, but not a 3D one. So I have another image. Where is it? Here. So again, sorry for the quality, I'm just taking it out of Google image search to quickly show you guys. So here if you have our W's here and P's here with our loss on this axis, we want to find the point of the W value and the B value where the loss is minimized. So this is what we want to do. We have L as a function of W and B, and we want to minimize L. So how do we do this? So for this, let us consider this equation. P equals A minus gamma del F A. So what does this equation mean? Let's take a simple scenario. We have our loss here, we have W and B here. So imagine we are currently at B. We want to find the direction to reach the minimum loss. And for now, like for the sake of the argument, imagine we want to take tiny steps. So we want to find ourselves in this location. So we are currently at A and we want to go to B. We want to move a little bit towards the ideal solution. So how do we do this? In order to do that, we want to find the gradient at our current location, which is signified by del FA. So if we find the gradient of the current location, then we can move along that gradient, which means we will be able to reach a location on the curve which is better than our current position. However, we don't want to go in the positive direction of the gradient, we want to go in the negative direction of the gradient, right? So we don't want to go there, we want to go here. So that is signified by this negative value here. So let's call this a negative direction of the gradient. And of course this is our starting point, so we'll be going from there, so that's why we subtract the gradient from that starting point in order to get to our endpoint. Let's not call it the endpoint, our next location. Now you may be wondering what this gamma means. So gamma here is what we call the learning rate. Imagine if you find the gradient here, and you find the gradient, and then you get to know, okay, it's in this direction, so you go you go quite a lot along this gradient, and then you end up somewhere here, which will give you a loss of this magnitude, which is much higher than our current position even, and we have overshot, having missing our target destination. So that's why we are interested in taking these like teeny tiny steps. So that's what we do with the learning rate. We choose a really small learning rate. So you see, like learning rates are like 0.1 or 0.01, something like that. So it depends on the problem. Like these are what you call hyperparameters. We may talk about these concepts later, but we are interested to take a really small step, so we will choose a really small learning rate. We will for now we'll choose these learning rates empirically. We'll try different rates and we'll find something that fits our purpose, right? So having explained this, let's go and see how we can calculate these gradients for our mean squared error. So we talked earlier that mean squared error is 1 over n, sum of I equals 0 to n, yi minus y hat I squared. So this is our mean squared error, which is again our loss, right? And we talked that we want to find the gradient of loss, and this is with respect to W and B. So we can call this delta L over delta W and delta L over delta B. So these are the partial derivatives that we want to calculate, right? So maybe if you are familiar with calculus, or if you want to give a try, you can pause the video here and do the derivation yourself. And if not, that's okay. You can join me while I try to derive this, right? So here we have our L, and we see that this is in terms of yi, and let's write the equation for yi as well. Yi is equal to wx plus b. So in order to find delta L over delta W and delta L over delta B, what we can do is to use the chain rule in calculus, so which is delta L over delta W is equal to delta L over delta y hat times delta y hat over delta W. And similarly, we have delta L over delta B is equal to delta L over delta y hat times delta y hat over delta B. So these are basically what we need to find. So if you find delta L over delta y hat and delta y hat over delta W and delta y hat over delta B, then we are set. So let's take the easy one, right? We can calculate delta y hat over delta W. So it's basically delta over delta W W x plus b. So basically this will go to 0 and the derivative of this is x. So double y hat over double w is equal to x. And similarly, double y hat over double b, in this case the first component goes to 0 and double b over double b is equal to 1. So this is going to be our solution for these two parts. Now let's go and see how we can calculate the rest of it. So we are interested in calculating double L over double y hat, right? So in order to calculate this, first let us consider double L over double y hat I, right? Or let's to make this a bit clearer, let's call this yj. Okay, so we are interested in finding the derivative with respect to just one element of that prediction vector. All right, so let's see. We have our loss function L is equal to 1 over n sum of I equals 0 to n yi minus yi hat squared. So we have double L over double yj is equal to double over double yj. Okay, what we can do is we can take out the constant. So 1 over n double L over double yj, we keep our summation as it is, but then we expand our square. So yi squared minus 2 y hat I yi plus y hat I squared. So in this case, let's in green I'm just going to analyze this in green colored pen. So okay, I missed an important thing here. These are all hats, right? So yi squared is completely independent here, so this will go to 0, and then we are left with two components here. And see that when I is not equal to j, all these do not rely on yj, right? So whenever I is not equal to j, this part also goes to 0, and when I is equal to j, this part will be 2 yj, because now I is equal to j, and then this part will be, we can take to front y hat I, right? And we miss this negative mark here, so minus 2 yj plus 2 yi. So this is how we are going to differentiate this, or this is how we are going to take the partial derivative. So let's erase these things for now. Maybe I'll keep it on and I'll go to the next page. So now in this new page I'll erase it in case you want to see this in the derivation in the slides. I'll leave it like that. Okay, so now we know W L over W y hat j is equal to 1 over n. The summation will be resolved as we explained earlier, minus 2 yi plus 2 y hat, so yj plus 2 times y hat j, and this could be simplified to minus 2 over n y hat j minus yj. So now that was the answer for L over yj was equal to minus 2 over n y hat j minus yj, and we can say that L over y hat, this is the vector, just make it a bit thicker to indicate that this is the vector, is equal to minus 2n y hat minus y. So this not really our final solution, but this is the more important part of our solution. And now using our previous calculations, we can say that L over W is equals to minus 2 times minus 2 over n y hat minus y times x, and L over B is equal to minus 2 over n y hat minus y. So these are what we will be using, right? So I just realized that I was covering the calculation. So okay, so this is what we have. So we will be using this in order to calculate our error and in order to do the gradient descent. So I don't want to make this lecture quite long, so let's go into our notebook and see what we have there. Alright, here we have it's not the analytical solution. Well, we have the analytical solution here as well, because I wanted to analytical solution. Let me edit this. Analytical solution and gradient descent. So we built the model as usual, read the data and pre-processed the data. So I'll be uploading this notebook so you can have a look at it. I'm not going to go through this part again because we did a couple of exercises in pre-processing the data, visualizing the data, all these things. So I'll just describe what I'm doing here. So we explode the data, explode the correlations, then I even built an analytical model and calculated the weights for the analytical model, evaluated it, and as you can see, errors were not that good, right? So we are going to do the gradient descent from here. So warning, this dataset is a simple dataset, but it's very hard to get it correct. So our loss will be quite big as well. And you can search in the internet for even more sophisticated solutions, but still, like, the accuracy is not that good. But this is a good example to show how gradient descent works, and I'll show how I did this. So I initialized two functions here. One to calculate the loss using the variable, using the mean squared error as I described earlier in the theoretical part, and then I calculate dl by dy hat. So that's the more longer calculation that we did earlier, right? And if we know this, we can easily calculate dl by dw or dl by db. So we have two functions taking care of that. And then we initialize the parameters, so just random numbers for w and 0 for the bias. And then this is to just store the losses and the accuracies, and we are running this for 1000 epochs. And we consider our initial learning rate to be 0.2 and our final learning rate to be 0.01, and we introduce a decay into the learning rate. So each epoch our learning rate will decay as it goes. So we run a for loop for the number of epochs, and first we calculate the model predictions. Then using those predictions we calculate the loss. This is the mean squared loss, and we calculate the dl over dy hat using the equation we proved earlier. So now we know the loss. Now we know the loss, and using that we calculate dl over dy, and we now know the gradient. And using that we can calculate the gradient for w and b's separately. And we calculated the gradient for w by multiplying dl over dy by x, training data for the x. And for calculating the gradient b, we just sum it up across the axis to get it, because we are looking for just one bias, right? And we update our learning rate using the per epoch decay, which we calculated up here. So using that we calculate a new learning rate, and here we update the parameters. So we say new w is equal to, so here you know what we say is w is equal to w minus, here we have the learning rate, which was gamma from earlier, and what was it, like del of our function f, which is the gradient w, right? So this is the equation which we are using. So we calculated the new w and the new b, and then we documented for every 20 epochs we documented our epoch number, the loss, and the current learning rate. And then we continued to do this for 1000 epochs. So we can say that as we go on, at epoch number 0 the loss was 0.07, and it reduced slowly at first, and then you can see that it reduces like by a really minute amount as we go ahead, and it got stuck somewhere here. So maybe if we can try to see what happens if we change the parameters. For example, the learning rate. Let's see if we have a bigger learning rate. Let's see what happens, right? So let's change the learning rate from 0.1 to 0.1 and see here what happened. We started with a okay loss, but then it became huge after 20 times, and then it went up to infinity. And yeah, so you can see that it became a huge number just because our learning rate was big. Let's say 0.5. So it still again overshot by a huge amount, 4.9 to the power of 4.9 times 10 to the power of 18. So this is again huge, which is not something we want, right? So let's go back to our 0.2 to 0.01. This should give us something like last time. Yeah, we'll go to up to 0.007. So this is good. Now let's try the other way around. Like, what if our learning rate is like really slow? So 0.001 to 0.001. So you can see that the error here is it started by 0.1 and it reduces, but it doesn't reduce far enough, right? So this is what I meant by like needing to calculate the hyperparameters such as the learning rate empirically sometimes. So, and let's see how our training accuracy is. Oh, for this one, like it's actually not good, very good at all. So actually this is not the training accuracy. I'm not printing the accuracy here. Let's print. So yeah, so this is same as the loss up here. So there you go. Like, please do play around with this notebook and try to redo the math of the gradient descent algorithm. And in the next video we'll probably talk about logistic regression and using then like we'll go on to calculate the gradient descent for logistic regression. And after doing a couple of exercises in linear regression and logistic regression, we can probably move on to another supervised learning task. All right, and thank you very much for watching the video. I'll see you in the next lecture.